Thanks, Giovanni, for the nice introduction. Actually, because I have an introduction to my group, you already saved me a few minutes. Good morning, everyone. Very good to see many young people here and all the colleagues. When I was invited to make this presentation, I felt very honored. CLAWAR is a great conference, but I asked actually to Manuel Silva, we all missed that he's not here, and he was the one who sent me the invitation. I hope he's listening online. I told him, well, but I don't do climbing and walking machines. But he said, don't worry, because the conference now is more comprehensive. And in fact, I was even checking it as support technologies for mobile machines. That's what I'm going to talk about today. And this work is a work of a team, as always happens in our areas. I put there the names of everyone who participated in the development of the robots that I will be talking about here. And there's a research assistant with a postdoc, Mason, Rui and John are PhD students. João was a master student. José and Rodrigo finished their masters, and they are research engineers with us. And Alberto Val is a colleague. He's the only one who's not with ISR, but works with us. And yeah. My talk, by the way, I forgot to mention that. My talk will be mostly focusing on practical aspects. I could bring here, and sometimes I've done it, I like to bring the formal part together with the applications. I thought it would suit well the conference to talk about things we have been doing recently on outdoor robots, particularly unmanned ground vehicles. That's what UGV means, but also with UAVs, and also starting putting them together, cooperating. And I will show you mostly not so much some of the things we have been trying to do on the top of it, more formally, more research-wise, more science-wise, let's say, in the PhD thesis and so on, but all the moments of development, because I thought this would be interesting to show, lots of videos and so on. So I will just briefly present first, we'll present first my group and what we do, and this is part of the motivation. And then I will have two major parts. One talking about multi-purpose mobile manipulator that we have used in the MBZIRC competition that Professor Muscato mentioned. And then we use that one together with UAVs in a European project where we do inspection of photovoltaic plants. And then I will draw some conclusions on future work. Okay, so as it was said, I'm from IST, which is the largest engineering faculty in Portugal and is part of the University of Lisbon. And there we have a group of research called Institute for Systems and Robotics, where I lead this group, which is there, the intelligent robots. Oh, this does not show there. Well, the people in the Zoom will see. The Intelligent Robots and Systems Group. Does this work? No, okay, no problem, no problem, no problem. We try in our group to approach systems from an holistic standpoint. What this means is instead of focusing on navigation or vision or some other aspects of robots, we try to look at the systems from an integrated viewpoint. Though we have, of course, some focuses like everyone, particularly on planning under uncertainty, also on applications that involve multi-robot systems and robots which are networked with other sensors. And we have had, as you can see in the pictures on the right, a lot of applications indoors. We had and still have robots in hospitals, at home. I've been very active in competitions, and so that's one of the reasons why you see there the football robots on the bottom right. We are not doing that anymore, but for many years we did. And then we also developed some outdoor robots like the one you see there in the middle, Raposa for search and rescue. And on the left, it's already part of one of the applications I'll show you in the solar farms. A lot of our research, and I mean really research, not just education, but also that, has been driven by robot competitions. It's a passion of mine. I've involved a lot of people from all degrees, from volunteers to PhDs and postdocs, and particularly in RoboCup. Also in the European-driven competitions that started with ROCIN and then the European Robotics League. And lately we had a participation on MBZIRC in 2020, which, as I said, is one of the things I will show here today. And I really think, and I think this is a message for the people here participating in the Volcano conference, that competitions are a great motivation for a lot of things, to learn more, to learn to work as a team, to learn to work under some pressure, and to be motivated to solve a problem. So it's important for education, for research, and I salute all of you. I will try to go there and see what is going on in the Volcano competition. Okay, so a brief motivation. Why cooperative heterogeneous robot teams? Well, the thing is, if we mix UGVs, unmanned ground vehicles, and UAVs, unmanned aerial vehicles, we can bring some advantages and cover the disadvantages of each of them. The UAVs have limited energy, but on the other hand, they can, particularly for surveillance operations, which is what we are talking about here, they can have an overview much larger of the scene and fly around and so on. On the other hand, the UGVs can take closer views and detailed views of the things. They have a much larger autonomy, and in fact, they can even help the UAVs to keep their autonomy by recharging them, which is one of the ideas that we have been developing. Also, another thing we have been pursuing is to endow particularly the UGVs with multi-purpose abilities. The idea is that they should be quickly changed in terms of hardware, take advantage of a lot of the software and also of the hardware, and apply them to completely different things, which is hopefully what I'll convince you today with my presentation. The competitions, I said that already, and so I won't take too long in this slide, but particularly what I would like to emphasize in this one is the fact that they push the state of the art in particular areas by bringing, instead of, which is also, of course, a very good and traditional approach, instead of having the people developing their work in particular cases and advancing also the fundamental research. Here, it's like another paradigm. You go to solve a problem which is common to everyone, and you compare the different approaches, the pros and the cons in several different aspects. And usually, if they are well done, they challenge you to do better every year, and they have very challenging experimental settings which try to be realistic. And I'm showing there several of them. On the left, it's the typical football field of RoboCup. In the middle, it's in an apartment we have at ISR where the robots can evolve and interact with people. And on the right, it's the project that is finishing as we speak, the European project that, among others, had competitions in big urban areas, in shopping centers, in museums, where the robots interacted with people which were not engineers or roboticists or whatever. So it brings much more realistic challenges. Speaking of challenges, let me tell you about the two challenges of MBZIRC 2020 that we faced. Because then I'll show you our approach and how we tackled them and how we used the multipurpose mobile manipulator for that. Actually, we were teaming with the University of Seville and the CATEC, which is a tech transfer center they have in Seville. They were in charge of the UAVs, we were in charge of the UGVs. Some of these tasks, these challenges involved the need to cooperate. I will be showing here only our part, but in fact, there were parts that the UAVs also did. So in challenge 2, the idea was to build a structure, which is like a wall with a set of bricks of different colors and sizes, and the robots would receive the pattern that would have to be built immediately before starting their run. And so they had to go pick up bricks from piles for each of them, for each color and size, and then put them one by one in the wall according to the pattern. And in particular, the UGVs were supposed to build part of it. The UAVs also could help. We could distribute things by them. No team could do many bricks, so this was really challenging. But and in this challenge, we did not perform as well as in the other, but we could already develop some interesting things which I want to show you. our approach is here and consists of putting together navigation, object perception, and object manipulation. You see some pictures of the simulator we developed, then I'll show you real stuff, but these illustrate well what's going on. You see there piles of bricks with different colors and sizes. And the first thing was to decompose the wall pattern in the sequence of bricks so that then we could have the system running doing the sequence that was desired. So we did that. We had that decomposition. Then we had to do navigation collision free, because as we will see sometimes, even though there's not people, there are bricks falling on the ground, even from the previous competitors, which we have to avoid. And of course, then detect the bricks, localize with respect to them, align with them, pick them up, take them to the wall, find the place according to the prescribed pattern, and place. So it's a pick and place operation, a bit more sophisticated. Place them there. In challenge 3, what the teams had to do was everything is autonomous here, what I'm talking about. So no teleoperation, robots are fully autonomous. To extinguish simulated fires in a building with a tower and with a less tall building on the right. And so they had to find these fires, quite realistic but not real fires, fortunately, and extinguish them. Okay, so and in fact to extinguish them, they really had to have water and pumps and hoses on board, because what would happen is that there would be meters to measure how much water we had poured into it to simulate or to emulate that we were extinguishing the fire. In the particular case of the UGV, so you see that tower over there, you see the real one, but there's a building on the right which is not there. And the UGV had to go inside that building. And while the other fires were in the tower, in the windows and inside, in that case, all of them were inside the building. There were 2 possible spots, and we had to find, usually only one was at a fire, we had to find the right one. And here we had more functionalities, but you can see that the mobile manipulator we were using, and which I will describe in a few slides, is the same with few modifications. And essentially, we have again navigation. Navigation implies that the robot has to localize, but in this case, it has to do a part outdoors of the building and another part indoors. So we had to switch. And then things more specific of the application, like the fire detection, aligning with the fire, calculating the distance of the shooting of the water, doing the water shooting, and planning the motion of the manipulator and of the mobile robots. And so, again, collision-free navigation, but now with a switch from outdoors to indoors. Then collision-free indoor waypoint navigation, which uses a different method. We will get there. Fire detection and putting out the fire. Okay, so let's focus on the mobile manipulator that we used for these 2 challenges and on particular aspects of it. This is based on actually quite old mobile robot that we had acquired in about 20 years ago from iRobot, the iRobot company. And then what we did together with a Portuguese SME, which is a spin-off of ours, IDmind, was to modify it thoroughly. So the only thing that was left were the motors, the wheels, of course, the chassis. All the rest, the electronics, including power, computation, was completely modified. And on the top of that, we acquired a brand new UR5E manipulator, 7 degrees of freedoms with force sensors, force and torque sensors, and we assembled it on the top of the UGV. And also it brought station and electronics for working in standalone mode. I mean, located on top of a table. Here it had to be on the top of this, and it had to be powered not by AC power, but by the batteries of the robots. And this was also done by IDmind, and it works flawlessly so far, which is very good. Well, I won't go into details, but you can see we have an idea of what was going on inside the robot. So you have a lower part with batteries, the motors, the boards for the motors, and then there's a door that closes on the top of that, and you see the rest of the electronics, which includes a CPU, which is a NUC computer, for those of you who know, and several things regarding the power conversion, the connection to the manipulator. And looking from outside, just to point out the important things for what we are talking about here, The manipulator has a real sense, which is one of the many variants that exist today of RGBD cameras like the Kinect that many of you may know. It has a GPS receiver, inertial measurement unit to determine the acceleration, the rate of orientation change. Then it has on the front an Okuyo laser scanner that does scans to determine the presence of obstacles, but also helps in the navigation, as we will see. And in this particular case, it has a magnetic gripper, though this is one of the things that changes from challenge 2 to 3. Here, the magnetic gripper was used to pick up the bricks because the bricks had a metallic plate that the robot could pick using a magnetic gripper. Functionally speaking, so how do we put all our functionalities together? Essentially, there are 4 modules. Perception, that, and this is very common in robots, as many of you know, others maybe don't, and so that's why I'm going into some detail here. The perception module gets the images from the RGBD camera and the scans from the laser, the 2D LiDAR, and processes them to provide information to the other modules. One important information is the detection of obstacles to avoid them. So remember I said we were doing collision-free navigation. The other one is also the environment scan, so that, for instance, we can compare what we see with the scan, like the distance to the different walls here, with a map of this room, and this way determine our localization. And also the events that go to the planner, because the planner does motion planning for the arm and for the mobile robot, but it also does a part which is not planning anymore. It's executing a plan which is going through the states of a state machine to go through different parts of the task. I will show you that. The navigation module, of course, is quite important. It is the one that moves the vehicle around. So it gets all this information plus GPS and IMU, fuses everything, and we will see, particularly in the final part of the other application, that we have been doing some new stuff on the top of the more traditional GPS plus IMU plus odometry, and determines the velocities that go to the wheels of the robot. Okay. Oh, I forgot, the planner does the motion planning for the wheels and for the manipulator, which then determines the motion of the arm, of course. So here's the state machine I was talking about, which is pretty simple, but it's important to make it work in real time and with all the information we have from the sensor. So essentially for this challenge, if you start there in the begin block, you go down, go to waypoint pile, and then you go to the left, align with the pile of bricks, pick a brick, the one that you want, of course. So each of those boxes has a lot of processing inside. Go to the waypoint, which is close to the wall, align with the wall, and place the brick. Again, the waypoint is not predetermined. It has to be, determined from the sequence of the pattern of the bricks. And so it changes from iteration to iteration. So it goes again to the waypoint and continues. We have used the ROS state machine library SMAC to create the state machine and to manage the execution of the plan. Okay, so focusing on some of the subsystems. This one here, the images are 3 times the actual velocity. This one here shows experiments we did at the campus of IST. We took advantage of the pattern, which allows us to visually check if the robot is following what we want, which, as you probably can guess, is those black lines that is currently going through. And what we were using was GPS, fusing it with the inertial measurement unit and with the wheel encoders. And at some point, not in these experiments, by the way, but later on, we also use the real-time kinematics GPS, RTK GPS, which improves the precision of the GPS. Well, this is a pretty open environment, which makes the life of GPS easier. And we used an extended Kalman filter to fuse all this information after doing transformation from the coordinates that the GPS gives us, which are latitude and longitude and altitude, into the frame that we were using locally. On the left, you can see evolving over time together with what's going on in the different images, the estimated path of the robot with the ellipses of uncertainty associated to it. And to be honest, I don't remember on the top of my mind all of those over there, but it's very clear that, well, the blue one is just the GPS data. And then there are different methods where we keep adding odometry, IMU, and you can see, for instance, that there's one which is completely misaligned, which is based only on odometry. As it is well known, odometry degrades over time, and if we would only rely on odometry, we would be dead, and after a while, the robot would not know where it is. But you can see that it does pretty well in the other parts. So we use this in Abu Dhabi for challenge 2. You can see on the left pictures of the simulator that we were using in Gazebo, and showing the cost maps that show the distance to the obstacles so that we avoid them. And you see the robot moving from the home position. It avoids an obstacle which has fallen from the brick over there quite nicely. So it does it a little bit slower to be careful, and then goes ahead. And then we will see in the final video, it goes to the other side to pick up the bricks. Just for the record, we use the global planning method, which is the Dijkstra algorithm, the one that determines the path, and the dynamic window approach for the local planner, which basically determines straight lines and circular arc motions towards the local goalpost, taking into account the available velocities and space which is free in front of the robot. One thing that we developed on purpose for this, and which was quite useful even later on for other applications, was to use the laser to get the robot aligning with the bricks. It is very important because the robot needs to align with the brick so that then the camera, which is the real sense camera, which is on the top of the manipulator, can see the brick and determine where it should really go to catch it. There's always small differences, of course, from run to run. And essentially, there's a line extraction you see up there from the laser scanner. The robot moves so that it gets at a given distance of the brick and aligned with it. So essentially, it is computing the brick's relative pose, and then it aligns with the brick based on a closed loop controller that uses that information. And then afterwards, it picks it, but we have not gotten there yet. And yeah, that's the part here now. And still, these are experiments that we did at IST. Oops. I pressed the button because there's a video that should run. Yeah. So here we use, as I said, vision. You can see there on the right several images which were processed. I mean, it is relatively simple because these are just single colored and dimensions that we know a priori bricks. The problem is when we go to outside because there are fluctuations of the light, and this causes troubles. And so what you see there is the brick doing, well, is the UGV doing, well, just repeated several times the operation of finding the place where it should put the brick, which is to the right from this viewpoint, to the right of the red brick and on the top of the blue brick. And it uses the magnetic gripper to pick up the gripper, makes his life much easier. But it has all this processing of vision, including edge computation, to know exactly where it should go and pick up the brick, which is very important, particularly for big grips, because then they can, as you can see, they shake a little, they can shake a lot and fall. Yeah, we did a lot of simulations. I'm not going into too long for those. I prefer to show the real stuff, but just for you to see that this is very important to pre-develop the system and at least make sure that it is working from a logical viewpoint. So you see here the robot doing all the operations, going to the brick, aligning, picking up the brick, going to the other brick where it has to put it on the top, aligning, and now putting it there. And this was working, and in reality, it also was doing this. You can see here, now still in our campus, the robot picking up a grip. It is almost aligned already with the others, but still it has to do some alignment with the place where it is going to put it, and then it puts it there. So this involves several things which are very important in a robotic system, and I wanted to emphasize that. It's the fact that you have to do each of these operations, you have to put them together, you have to react to events, you have to, even in some cases, if there's a failure, react and try again or do something else. And all of this should be part of the system. We did this also in Abu Dhabi. So this is indoors, much larger space and a much larger brick. and then the place where it had to be put is hidden now, but it's on the left there. And on the right, you can see it in the real scene. I'm not sure if it shows there, it will show later. We had troubles in the real thing because of what I said before. The light was, I mean, we could not train it before, and the light there was creating troubles because it could pick up the brick, but not so well like here, not in the middle. And as you will see here or later on, I'm not sure now, then the brick falls because of that. So that was a thing that was not successful. There are failures in robot systems. But here, as you can see, it could do it pretty well. So the problem was a perception problem. Well, yeah, exactly. Okay, challenge 3, other systems, other type of composing them. Particularly here, what was somehow more interesting was the fact that we had to mix outdoor and indoor navigation. And so that map you see there was built using a SLAM algorithm and shows an external part and an internal part. So outdoors, we could use GPS, IMU as before, and odometry. Indoors, we could use a map, and first of all, we could not use GPS, but the map was also very reliable. We were very used to do that in other applications I show you in the domestic and hospital environments. And so we did that. And while outside we were using extended Kalman filters, inside we used the Monte Carlo localization, so particle filters. And there we really used the scale, the laser scan matching in order to do localization. But of course, this poses a problem, which is when you move from one environment to the other, you have to make sure you detect that so that you switch the localization. Then this switch that provides the pose either from adaptive Monte Carlo localization, AMCL, or from this other package robot localization, which is based on a Kalman filter and fuses odometry, IMU, and GPS. Then particular things of this challenge. We had to do a fire detector and we used a machine learning very popular algorithm, which is Tiny YOLO, and using an RGBD image and also a thermal camera, because there were 2 points. One was the simulated fire. That one is the type of what was used in Abu Dhabi. We walked one and were training it in our environment. In fact, the algorithm was trained with real fires and with this type of simulated fire. And so it worked well because the fire looks very realistic to the computer, to the machine as well. And then we also had, so for first detecting the spot, but then we had to determine the hotter spot with a thermal detector, because this was important, as we will see, to shoot the water at the right place and really feel the deposit that it was desired. This is actually the real scenario in Abu Dhabi. So you can see up there, there's inside plexiglass, there's a hole, and there's the place which right now has no fire, but which is hot when the fire is on. And so with the camera, we had to find it, and then we assembled these hoses and deposits on the manipulator, and we had to align this correctly by finding that place. So another thing to put in our task and to coordinate with the rest of the tasks, which is something we like to do, to integrate all these aspects, as I told you in the beginning. And curiously, on the right, I'm showing you the alignment with the bricks. Was very useful to do the alignment also here with the place on the top of which the fire, the simulated fire is. And I mean, then also a simple control aspect to control the distance to the wall compared with the distance we want. We want to get a given distance so that then it makes our life easier to do the computations of the angle to do the shooting. We knew we had the calibration of depending on the angle where the water would be going at a given distance. And also we had, of course, to do this alignment, in this case, closing the loop with a thermal camera, so that we could point at both in terms of height and also on the lateral dimension, to point it at the center of the fire. We had an algorithm which actually one of the students had developed before for other purposes in his master thesis that we readapted here. So basically, the robot goes to a circle around the point where the target is, in this case, the fire. This is a general thing. And this point in the circle depends where the robot comes from. And particularly if it comes in this case from the left of the room, this is actually an image with the scan of the actual room. It finds a point over the circle, and then it aligns in the direction of the radius towards the point. And the radius is that distance I told you about. Well, this is just to show you the different ways of the water shooting working, sometimes better than others, but it was on purpose to show you the system working. On the top, it's not so easy, but down here you can see it. Then we also did a very thorough simulation of the environment. Here now you can see the high tower, and on the well, in this case on the left of it, the building, which is now on the bottom right in more detail. So that brown part on the left is where the fires are that you saw in the previous pictures. And then we had the task. Oops, I thought it was here. The task for challenge 3 was again a state machine where it goes to the door of the place where the fires are. It switches to indoors localization, and then it starts checking if it detects on the first possible point for the fire a fire. If it detects it, it aligns with the fire, shoots the water, goes to the door, leaves, and that's it. If it doesn't, it tries the second point, because there may be 2 possible ones. And also, if for some reason it does not detect either one, there should be one, it knows, so it keeps trying. So it's like recovering from a potential failure. And here we can see how we checked again from a logical viewpoint if the system was working. This is a simulation, but where you can see the arrows show the estimate of the localization of the robot. You can see those blue zones are the cost maps around the walls of the place where the robot is entering. This is in our lab. This is not the real thing in Abu Dhabi. And he has those waypoints on the right, the big arrows, where he wants to go. He already starts watching the place where the fire is. It showed there for a little bit because it saw the device there. It aligns. Now it goes on the top of the circle and aligns with the fire. On the left, it's not easy to see, but it's not easy to track, but you can see the state machine and the different states evolving and going through them as it goes. So all this we could check if he was doing right. You see now he detected the fire. He knows it should go on a circle with that radius of the distance with respect to it. He's trying to do the motion, which is difficult because it has obstacles nearby, and it aligns with the fire and shoots, well, not here, but it shoots the water. And in fact, this is what's going on in the real environment in our place. On the left, you see the map, and in red, the readings of the laser showing that the robot is very well aligned because it sees the walls where it shoots. So this is based on his estimate of position. And we simulated going from outside to inside. So now he's using already, oh, he's jumping the video. You see the simulated fire. He is going to a waypoint, then he's going to search for the fire. He sees the fire, and he goes too close, so then he comes back to recover that distance. So all of these things are based on closed loop information, event detection, measuring distances, aligning angles, which is very important if you really want the system to be dependable and work and not just be pre-programmed, which might be problematic. Oh, that's really strange. Okay. That's the scenario. They built an impressive scenario in Abu Dhabi with the big tower, real stuff in a big stadium, and on the right, the building. This is our robot actually evolving there, protected because the water could power on the top of the electronics. So it looks bad, but it's really necessary. Also, you can see on the left one of the simulated fires that had to be put out with a blanket. Could be with a UGV, but we decided to do it with UAVs, and actually Seville did that part quite well. And then on the right, you can see again the image of the place. So I'll show you a video, which actually I won't talk much because it is self-explanatory, but here and there I'll point out. which shows you essentially many of the things I showed you before and what we did also there in Abu Dhabi, and summarizes the different achievements of this multi-purpose mobile manipulator. So this is the what we call the pick and place cycle, and all the different steps I told you. So look at the captions in the bottom. So now it goes up. I did not emphasize that enough. He goes up. He always goes up, not just to get some space, but also to have an overview of the scene, like here, to be easier to determine the different things it needs, like where is the brick it should pick, where is the place where it should put it. And that's why the manipulator goes up to give this view to the RGBD camera. Okay, so I'll just move this one. You have seen already. Well, I would move if I could, but I don't think I can from here. No problem. So he's doing the same now in this other environment, already at Abu Dhabi, but here just for training. Is there a way I can speed this up? I mean, moving in the video, I don't think so. Ah, yes. I was missing that. Okay, so now you can see it. We saw part of it, but we should see a little bit more. So it actually did that failure that you saw before, because, but then I think it's here, it tries again. And actually it was slightly more successful, but then lost it. But you can see what happens now when it turns, because instead of being exactly in the middle of the brick, the grasping was made on the sides. Yeah, and that's why it's more difficult to pick it up. Okay, so then this is the trials we did at our place inside, and all inside, but emulating being outdoors. And now I wanted to show you this part you saw already, detecting the fire, moving into position. Now it's better than before, so maybe we should see this. And shooting the water on the fire. Doesn't shoot the water here, of course, but it gets back and then it moves outside the building and completes the mission. Now, we did this, and this is what you did not see before, in the competition setup. These are the 2 points of fire, the one on the right, this one on the left. So the two possible fires that we had to go close to. So it first does the navigation outdoors. It detects when it is in front of the door, and then turns. And when it crosses the door, it detects it is inside and switches to the Monte Carlo localization method. So this is actual speed in this case. And now we could not see, we could not be there, but we could see with the cameras that were installed by the organization inside. And you can see it going to the first waypoint to check if there's a fire there. You can see there is no fire there. So it will detect that there's no fire with the thermal camera. And then because of that, it goes to the second one. It finds a fire and it will throw the water that we can see in the meters that will show up in the bottom, that it's they are being filled, especially this one on the left. And actually we did this motion also to compensate for small failures that we could have. Well, and we won challenge 3, so that was very successful. Okay, so moving to the, how long do I have? Okay. We actually, when we engaged into that with Seville, we wanted to go for an European project that we had in mind. And we were developing the technologies, of course, because we like to be in that competition, and it went pretty well. But because we wanted then to apply it to some kind of even more realistic scenario, which in this case was the inspection and maintenance of solar energy systems. And this was a durable project, which in fact also concerned wind towers and wind energy. But we focused only on the solar part. We were responsible by the UGV part, but we did some stuff also with the UAVs, and this is where I will show you some cooperation. There were, as you can see, several partners from the Atlantic region. This was not an Horizon Europe, it was an Horizon 2020, was an Interreg Atlantic project. And one of them was the Portuguese company, the power company, EDP, the largest one. And so the concept was, and still is, we already did part of it. The project is just ending as well, but we want to try to extend it to another project to continue, to have a team of UGVs, the red ones, and UAVs, the black ones, that keep inspecting autonomously the solar plant, particularly to find defects and that need replacement in the solar panels. And the UGVs, well, the UAVs do the inspection, they have cameras, they keep flying around. They need to recharge from time to time. So they go on the top of some of the UGVs, which are recharging stations. And some of the UGVs, in particular ours with the mobile manipulator, can also do inspection in the lower parts of the panels with more detail. That's the concept. We did several things in the labs, and then we went for a few demos in one solar farm of EDP in the south of Portugal, in Alentejo, in Évora, and there we did several tests. On the benefit of time and also to leave time for questions, I won't tell the details here because then I can tell them in the video. But there were several things regarding navigation, again, of the two UGVs we had. So we added one, the UGV Jekyll from ClearPath to the one I showed you before, but also parts of the manipulation where which is used to do inspection with thermal cameras, and collaborative stuff between UAVs and UGVs, particularly landing on the top of an UGV, an UAV following an UGV, and also some remote operation using a so-called virtual cockpit system. The autonomous navigation was again the same idea that I showed you in the Abu Dhabi competition, but also here we had the waypoint navigation for the UAVs. So the UAVs could follow a predefined path using mostly IMU and GPS, so they could go over the top of several solar panels. And UGVs were using GPS plus IMU plus odometry plus something else, which I'll tell you in a minute, which was one of our innovations here. That something else was to take advantage of the scan. So the map we did inside the building in Abu Dhabi, we could do a map here with the panels. In fact, we acquired a 3D LiDAR Velodyne, which is quite popular these days and reasonably priced for the quality it has. We assembled it in the other UGV. We did maps of the plant, and then we used that on the top of GPS plus IMU plus odometry to improve the localization of the system, particularly when the robots are in the middle of the solar panels, because there you can lose some of the satellites of GPS, since these are metallic structures, and it's well known that this is a problem. So you can see that we could improve the mean square error, the accuracy of our localization as we were adding more stuff. And we even did some things. We are preparing a paper on doing this matching. As you can imagine, this is a huge area, so we have to limit the area we match with. It is very symmetric, which is a problem, but given that we have GPS and odometry, the two things together work well. But also, even like that, there's a lot of points in the point clouds to match using algorithms like ICP. And so we did things like segmentation, which groups the points in the ground, the panels, the pillars of the panels, and then we do the matching between these groups and not with all the points, which makes the life of the algorithm simpler in computational times. We also did georeferentiation, which means that we can put our maps in UTM coordinates, meaning, for instance, that we can see pretty well using Google Maps exactly where the robot was in reality. We acquired thermal camera data that then another partner processed to find defects. These are images both from the top by the UAV and from the, say, the ground with the UGV and the camera on the manipulator. And we synchronized also this view so that then the UGV could go to a place where the UAV had seen a defect. And all these, I mean, the steps we did in that direction, it's not all integrated. And it's only the part of the robots. There's not even the part of the, there's not even the part of the processing. It's shown in this video. And in this one, I'll make a little bit more comments. For instance, here, this is twice the speed. The robot is moving outside and it's doing waypoint navigation, in this case with the GPS, odometry, and IMU. And it's also moving the arm because the arm is going to be used to do the inspection of the panels, as we will see. The tower here is the GPS, and we installed the tower exactly to make it a little bit higher to see the RTK antenna, which is in a building nearby, and try to avoid the influence the panels as much as possible. So as you can see, the terrain is difficult, it's bumpy, it's grassy. The robot still manages it quite well. Then it gets to places, I mean, we just cut it for the sake of being quick, but it really does it everything together in a row. So it goes to a waypoint, it does this predetermined motion of the arm, which aligns the camera with the panel and gets the images that then are going to be processed. This is the other robot doing the map. As it progresses, the map is being built. And then next you see the final map, just taken from the center. Unfortunately, the video is having some glitches, but just taking from the center corridor of the farm. So it's quite impressive how far the Velodyne can see. Then we, in later iterations, we did some turns to complete the map. And this is the segmentation. So different colors are different classes. And the robot is already also doing its navigation. So you see the estimated location of the robot and the point clouds of its observation. This is also waypoint navigation of the other robot using only GPS and odometry and IMU in the central corridor. And this is one of the nice things. So the UAV with a camera checking QR code, an Aruco pattern on the top of the UAV and landing on it, or the UGV, landing on it both when it is stopped and when it is moving. And this is what is necessary so that then if we install a charging station on the top of the UGV, it can recharge. In fact, we did some further experiments later on, so even closer to now, at IST. And here the algorithm was a bit more fine-tuned, and you see the UAV tracking, using vision, tracking the UGV, including the orientation. So it's always aligned and ready to land in the right orientation. And it does it quite well. And finally, I think it's the final part. Yeah. We also did something that looks similar, but then completely different. The UAV on the top is tracking the UGV on the bottom, but now, because the UGV is sending it by communication wireless, the waypoints. And then the UAV goes to the same waypoints. The last part looks the same, but in fact, the robot is being supervised or remotely controlled from France by a virtual cockpit that was developed by our colleagues at Estia. Okay, so to finalize, and in a simple slide to try to say a few things, we did some demonstrations of the ability of using multi-purpose UGVs and teaming up in some cases with UAVs to do surveillance operations that require teams. we are on the top of it, particularly now that the projects are over. Keep doing the practical applications, but trying to formalize some of these aspects. For instance, this is something we have been doing over the years in several theses. We developed stochastic Petri nets models to model the team tasks and to analyze their performance and to determine policies that maximize long-term average reward. We even developed a tool with MathWorks, which is now a toolbox in MATLAB to do this kind of stuff, and which then compiles into ROS executable code. And there's 2 ongoing PhDs, which are trying to formalize 2 parts of what you saw, particularly in this last application. The cooperative situational awareness, that is the different robots building the maps and the location of the other robots, of the plant, and so on. And how to use an optimal solution for the cooperative surveillance. That is to know where the robots should be at a given time, to do inspection, to recharge, and keep the full team flying. Okay, if you want to know more about the group and these projects there, you can use this, scan this code, and you'll go to our page, and you'll see this and many more things. And now I'm open to questions if there's still time, I hope.
Okay, thank you very much. We have a few minutes for some questions, if any. Any question from the audience? Yes.
Hello, my name is Thiago. I actually have some questions that I'll ask too. So the first one is the AI, the robots AI is supervised or not?
I didn't understand part of the question.
Supervised.
But he said the AI.
Yeah.
So the robot is fully autonomous. Well, these days, what is AI has a lot of definitions. I mean, there is, in the way people talk about AI, some AI in the fact that there's some machine learning algorithms for recognizing objects and the bricks in particular, and the points of the fire. The rest, I would not say it is AI because it's kind of a relatively simple state machine for supervising the execution of the system. But it has a lot of important details robotics-wise, yeah.
Okay, the other one is, does the robot already know what he's going to do, or the machine learning can identify the situation and already know what to do?
So in terms of the task, it knows the sequence of steps, but then everything depends on what it observes along the way. It has to do corrections, it has to align better, it has to sometimes find that it could not go the way it wanted because there's an obstacle and it has to avoid it. So that part, it adjusts.
Okay, thank you.
Okay. Other question? Yes.
Thanks for the interesting presentation. I was wondering whether you're having trouble, or like the way I understood, you have the intelligence camera mounted on the arm. Do you have any also problems with occlusion, or that you don't see certain parts once you pick up the brake? Basically, you have this sequence where
we assembled the camera in a position, and also this movement is done in such a way that it really avoids that, because we had troubles otherwise. And so where you can have some occlusion is when you pick up the brick and then want to put it on the top of others. And there what happens is that we first inspect both the location of the brick we are going to pick and the location where we are going to put it, plan the motion, and the last part in that sense has to be done blindly, because we cannot adjust anymore if we don't see the whole scene.
Any other question? Okay.
Hello. Little question about the visual detection of the bricks themselves. So how did the patterns, or how did the visual features look like that you oriented yourself doing the final picking up routine of your robots? So I've seen these white patches. Are those basically codes or visual features?
What happens is that we wanted, for instance, to find a green brick, but it had a metallic part on the top of it that we also wanted to segment, because we wanted to go and center the gripper with it. And this is, I'm not sure if that's what you were talking about. This is where sometimes the problem were, particularly if we hadn't the possibility, as it was the case, more people got similar troubles, to train it with images of this when you don't see the complete metallic part because of light directions, like the sun in that case. And when that happens, it determines the center of mass, let's say, in a different location. And that's why it went and picked it up in a different place.
Okay, thank you.
Thank you. Yes.
Like the idea of competition involve students to work and so on. On the other hand, there is a gap between competitions and practical applications. And my question to you is, how big do you think is this gap?
I mean, I think that in a lot of what we do, particularly in academic research, right, there's always this gap. For me, I agree with you. I mean, even when I showed there, even in that impressive setting in Abu Dhabi, there's a gap. Of course, I mean, we are not building a real wall. We are not putting out of a real fire and these kind of things. But what I'm saying is that even if there were exactly the same gap, I think it would be very interesting to have a challenging problem which is common to everyone and see what are the different solutions. But I think the gap is smaller, much smaller, in many cases like in that one, than if you go to the lab and do everything controlled and show your best video instead of kind of the average performance, which is what unfortunately happens a lot in robotics. And so the gap is there, but it's, I think, much smaller.
Okay. A final comment. I found very interesting the presentation, also because, you know, we also participate in MBZIRC, and we have also a project on inspection of a solar plant with the cooperation of UGV and UAV. And I think this example was interesting because you've shown in a practical application how to apply the result of something that you developed for the competition.
Exactly.
So in some way, this answer
addressing
your question, because and I found it really interesting, that one. And okay, so thank you very much, Pedro, for this presentation.
Thanks a lot, Jovan.
We have also a present from the organizer for you. Thank you again.